Hello, we will be doing a paper review of a preprint we have today. And so yeah, that's what this video is for. So, okay. So, a unified framework for generalized arithmetic, commutative operations, tropical geometry, and statistical moments. So, our preprint basically starts with these operations called, what do you say, Bennett hyperoperations. And one of the things we do in our paper is we draw a connection between Bennett hyperoperations and tropical geometry. After we do that, we take these Bennett hyperoperations and we rephrase all things in statistics, or like the basic things in statistics, in terms of these Bennett hyperoperations. So these, when statistics is reframed in terms of Bennett hyperoperations, we call them Bennett Statistics. And the hope with this is that we take Bennett Statistics and we should be able to study well-known families of well-known families of probability distributions using Bennett Statistics. And the method by which we want to study them is by using generalized moments of methods, so GMM for short. So this is what the paper is going to talk about. In our paper, the preprint that is on the left side over here, we talk about this part exclusively. So later when we write further papers, we will move along. The project right now is going to start focusing on this aspect. Okay, so to summarize what the abstract is saying, the abstract is just talking about Bennett hyperoperations. Now, the thing about Bennett hyperoperations is that it's a continuation of things like addition, multiplication. I don't know what the symbol for increment is, but increment, and so on. So it is this. Okay, so typically when you go from increment to addition, and from addition to multiplication, from multiplication to exponentiation, and from exponentiation to tetration, what you do is you use this argument of repeating the previous operation n number of times. So when I say a plus b, that means I increment a b times. Okay, so that's what it would mean, or like that's how you would climb the ladder of hyperoperations. So similarly, if I go down this ladder, let's just box this sequence over here. So if I go down this ladder, what would I talk about? Multiplication a into b is just a added to itself b times, right? And a added to itself b times, yeah. And so the trick about this argument of constructing hyperoperations is that the second you move from multiplication over here to exponentiation and to tetration, they lose commutativity. And so because of this loss of commutativity, generalizing anything to something that is beyond exponentiation becomes meaningless, because not only do numbers become very unwieldy, they also, okay, let me check the recording once. Seems to be okay, I think. Okay, so not only do they lose the fact that they're commutative, they also lose the fact that they're easy to work with. So addition, multiplication, if we rephrase any, try, if we say, the reason why we choose addition and multiplication is because they're easy things to model, they're easy things to understand, and they keep it simple with fewer number of elements. The second you try to model something with multiplication and tetracration, things become extremely unwieldy. For example, 3 tetrated to 3, 3 to the power of 3 is like fine. 3 tetrated to 3 is extremely huge. And so this becomes very impractical when we're trying to deal with smaller things. So the reason is because of this. What do you say? Not only there are two. Okay, yeah. Let me phrase this a little better. Okay. There are two things that make this line of thinking okay, I cannot draw circles for some reason. Okay, there we go, that's a big enough circle. So this line of thinking has the issue that it comes with two issues. It comes with loss of properties like commutativity, associativity, distributiveness, and so on. So because of all these nice properties being lost eventually as we go up higher and higher this ladder, and this is one reason why it's not what do you say, helpful. And the next reason is what do you say, okay, having large numbers wouldn't necessarily be a problem, but let's just note it down because this is something that sort of gets addressed by Bennett statistics. This is not to say that large numbers don't turn up often enough for them to be useful. This is for us to say that Bennett statistics, in comparison, Bennett statistics, by comparison, is, oh, sorry, I don't mean statistics just yet. I meant hyperoperations. So by comparison, Bennett hyperoperations don't have this issue of small numbers blowing up to much larger numbers. So this, I just want to pose it forward as some sort of like advantage, a potential advantage. It's not a technical thing. It is not an advantage per se, but it is a nice thing to have. We would like our operations to be well behaved and not go crazy the moment we go like 4 steps up a ladder. So let's talk about these, what do you say, the main operations of the event. So what are Bennett operations? Bennett hyperoperations. So it just rephrases everything in terms of saying that f of, okay, no, let's not talk in terms of f of n. So a plus x over here and m over here of b is the same as the exponent with the circle over here x taken log of m circle over here x of a plus log of m circle over here b. Now there's two things you don't know what means in this thing. So I've given you a definition, sure. This is our quintessential Bennett hyperoperation in action. You won't. What I haven't defined is what these circles mean just yet. And all I mean by these circles is that exponent circle of x of some a is the same as, since this is in base m, as you'll notice here, in these two places. It is basically m to the m to the m continued all the way up to a. So this happens x times, or in a much cleaner way we can write it as is equal to x x x a at the very end. And so this whole business happens x times. Okay, so don't worry about the specifics by asking whether the inside part happens x times or if it's really x plus 1 times. I just mean in the loosest sense possible that you're taking the exponent of your variable a x times. All right, similar thing for log m of x. It's the exact same thing, just replace exponent with log. So it's log m, all of this continuously until you get to a. Okay, x times once more. Okay, so why would we choose log and x? And let's talk about the choice of log and x just for a minute, because that's something that comes to mind. And another thing is, this whole talk I'm going to take liberty with going as long as I like, because I plan to use this as a revision whenever I do decide to present this to someone. So it just helps me keep, it would help me keep all of my points in the same video rather than having to juggle through my notes every time. So let's talk about why exp and log. Okay, so what we saw in our expression is that we said a hyperoperation. I think I put x on. Did I put x on top or m on top? Okay, it's fine. We know what x and m denote, so I'm just not going to worry about it too much here. So we saw that this is basically of the form f of x. Okay, this is done x times f inverse x times of a plus, okay, let's see if I can close this. Okay, I would have to use my mouse. Okay, this is being a pain in my ass. Yep, it seems hell-bent on not wanting to disappear. That's fine. It's okay. We don't need to worry about it. Okay, so you can see that our operations seem to be of this form, where f in this case is just our exponent. Okay, makes sense? And so let's note some things. It is clear why this thing clearly preserves commutativity, because as we make x higher and higher, which is sort of in some sense I'm climbing the ladder to higher and higher operations, you can see that underneath it all, this operation is still addition. So because of the fact that it's still addition, these two things can commute with each other, and so there's no problem with commutativity throughout this ladder. So no matter what the value of x is, commutativity is always preserved. Next thing, let's actually talk about what we said. So we want to understand why we're choosing log and exp. So after noting that this is of the form f and f inverse and all that stuff, and we saw that f over here corresponds to exp, we should consider different examples of f. So let's see what happens if f is equal to sine. So that would just mean that you have sine repeated of x, sine inverse of x, not of x, sine repeated x times, of sine inverse repeated x times of a. plus sine inverse repeated x times of b. Okay, so let's consider this kind of operation. So the thing that I want you to note is that let's simplify this for smaller and smaller numbers first. So let's consider small values of x and see what we get as a result. I have to scroll down again. Okay. So I'm going to draw the bar over here. I have f is equal to sine over here. I have f is equal to exponent over here. And I'm going to change my values of x as I go up and down. So over here I'm going to just put x in the middle. I have 0, I have 1, I have 2, I have 3, I have 4. Maybe we'll go to 4, depends if the point is clear enough. Maximum we'll go until 3 and we'll just see what happens after we go from 2 to 3. So what's going to happen is over here at 0, 1 and 2 you will see familiar operations, and the moment we come to 3, 4 and so on, you'll see what those familiar operations turn into as you go down this ladder. So in the first case, sine of x done 0 times and sine inverse of x done 0 times plus sine inverse of x done 0 times. So over here it's done 0 times, over here it's done 0 times. Let me underline, here it's done 0 times, here it's done 0 times. So that means inside it is a plus b because those operations are done neither times, and outside also this thing is also done 0 times, so that is just simply a plus b. For the exact same argument, our first term is just a plus b here as well. So this thing is true for all for no matter what the function is. If you're doing a function 0 times, it's simply a plus b. Next, let us go to the value being 1. So in this case, now I have exponent of log a plus log b. Similarly, I have sine of sine inverse a plus sine, okay, I'll write it down, plus sine inverse b. Okay, and so if we work this one out, hang on, let me just pause for a second. I can pause. Yeah, so the reason I paused for a second over there was because I wasn't sure what this one on the left would simplify to. So the one on the right simplifies to simply a into b. That is because it's log a and log b combine into log of a into b. And then you have the exponent on the outside, so you have exponent of log of a into b, and that exponent part just cancels out the log part, and so you just have a into b. Okay, this is the product rule of log thing. And on the left you have a much more complicated thing. You have, which is why you needed to pause and just figure it out. So this is what you get as a result: b root of 1 minus a square. So over here we see that we have one familiar operation, we have another familiar operation, and so it would be interesting to find out what happens next in this line. Over here we have one familiar operation, we have a completely unfamiliar operation, and this is the reason why I want to argue that exponent is a more natural choice to use for f. Theoretically, you can use anything that you like, because for all functions f, at least at x equals 0, you can just get the regular sum back. What you get here on out will also be commutative, I hope, because the underlying part is also commutative. So the only true difference we can expect is which kind of hierarchy is more well suited, or which hierarchy preserves more of the features that we like, that makes sense for us to generalize it in that direction. So again, I want to point out, because I want this to be like, something that can be discussed by other people. So f can be anything. But it shouldn't be everything. But it shouldn't be everything. Be everything. Okay. So with that justification, let's continue on what these operations are. So now I will actually move beyond the first page of the preprint, and we will see. Okay. So the first is just some random stuff I put about what these Bennett operations are, about their origins, about why they were useful before, because effectively there's only one paper that talks about Bennett operations in the way that they are. And so over here I've listed two things. We will show an application to tropical geometry. This is another paper of its own that I can explain now I've given this once I've explained this part well enough. So what I'll do is I'll finish this paper and then I'll circle back to this topic to talk a little more about its relations with tropical geometry. So we talk about Bennett operations in the context of tropical geometry. Then we redefine stuff in normal analysis, not normal analysis. We redefine stuff in normal statistics, and things like mean, moment, all those things moments, we generalize those. And once we've done that, we also extend Bennett operations so that they can apply to matrices. So we propose one operation, doesn't have to be the definitive one. There can be more different ways, more complicated ways to go about it. And well, here's a small spoiler that talks about the most natural way to go about it. So the spoiler is that since we can compute the exponent of a matrix and the log of a matrix using its Taylor expansion of log and exponent, you can go down that route of calculating Bennett operations acting out between matrices, but those themselves are pretty hard to compute. I would say it's impractical to compute on its own, like in the state that we are now. So I'm going to just talk a little bit more about how that could be like avoided. So some alternative ones that do not stay true to this definition of it, but may serve some purpose more or less. So yeah, let's first just talk about notation of these commutative hyperoperations. So Bennett. I keep forgetting if it's Bennett or Bennett. So Bennett hyperoperations and in bracket commutative. Okay, cool. So let's just get some notation. We want to have notation similar to summation and what do you say, multiplication. So we want this kind of notation to exist. So what we've defined is something that looks like this. Over here it's brackets because you can't draw a big oval and put letters in it in latex. So this is what, is that an X? Yeah, that's an X. Our hyperoperations would look like. So this would go from I is equal to 0 to n. This also goes from I is equal to 0 to n. This would also go from I is equal to 0 to n. The only thing is that this m and x will just tell you what your operation is. So summation is when m is equal to e, or m can be anything really. So we take e as a standard because e is more like, we all know that e is natural for logs and stuff. So just as standard, we take it as e everywhere. So whenever we can't decide what base works best for us, we just chuck an e over there. So, and the next thing is x over here is equal to 0 and x over here is equal to 1. Okay? And so in general, it's of this form. So whenever we generalize our definitions in statistics, we will be using this notation. Similarly, we've been talking this whole time about hyperoperations. Oh, my bad. Earlier in the video, I drew them as this. I'm realizing that now. This is the wrong notation. I'm sorry. This is the right notation. Okay, and so this would correspond to the sequence of plus multiplication, the next operation. So that would just be uh, e over here and 2, and then e over here and 3, and so on. Similarly, we have inverse operations like that are not necessarily commutative again. So we have minus, we have division, and so in this case we denote it like this. So we have e over here and 2, e over here and 3, and so on. And so if the general form of a hyperoperation is this dot thing, c dot thing with an x, m and x, then its corresponding inverse Bennett operation is this dash thing inside of a circle with an x, m and x. Okay. Now, I would like to point out that this sort of mapping, unlike this sort of way of traveling between the actual operations over here on this side to the inverse operations on this side, is not the same as switching from progressing this way to the up the ladder to going back this way. So uh, in a confusing turn of events, there are there are three things to basically worry about. So far I've listed the original operations. Where's my yeah, there we go. Okay, cool. So far I've listed my Bennett operation, which is just this. However, Bennett was only defined for x is greater than 0, greater than or equal to 0, and x is a natural number. Okay, this is how it was originally defined. And similarly, Bennett inverse operations were defined with this minus thing in the center with the exact same constraints over here. So what we do is we can extend the Bennett operations just to be able to because that's where the connection between this and tropical geometry lie. So the way we extend it is by considering x just belong to integers first. So how do we do that? We saw initially that our hyperoperations were defined like this. So we have a and b over here. This gives you exponent x times plus log x times of a plus log of x times of b. Similarly, when we want to define it for negative numbers, so say x is negative in this case, say a b over here, let's just assume that x is natural only so that this becomes a little cleaner. So in this case the operation thing is negative, in this case it's positive, just putting it there. Okay, so in this case we would have log repeated x times, and then inside you will have exponent x times of a plus exponent x times of b. So you'll note that I earlier pointed out that the inverse operations are not commutative, which is clear when you look at minus and division, and you can assume that it would hold for higher inverse commutative operations. So you can conclude that since here as well you're preserving your commutativeness, this is not at all an inverse Bennett operation. So it does not belong to this whatsoever. So really, as I've been saying earlier, it is an extension of the Bennett hyperoperations. The only difference is that initially the Bennett hyperoperations were only defined, say this is at 0, it was defined for 1, 2, and so on. The only thing is that it's extended to have to be like defined for -1, -2, and other negative integers as well. That's the only difference. So cool. Another thing that would be useful to generalize is this negative summation as well. So let's delete everything. Okay, cool. So as we were talking about earlier, we were talking about notation. So this is what our notation looked like earlier. This corresponds to things like summation and product. Okay, I'm just putting that there just so you can look at it. And we're just going to put a AI over here. Okay, so what this corresponds to, as you can see in the paper over here, it corresponds to A1 over here, MX A2. Oh, sorry, A0 was supposed to start with A0. So A0, A1, MX, and then A2, MX, and so on. Similarly, just so we have it present with us, the notation is just defined, just so that in case we ever need to use it. So similarly, we have just gone ahead and made notation for the inverse operation as well. So this thing corresponded to this, right? This thing is going to correspond to this. So this is equal to A naught mx like this, A1 mx like this, and so on. Okay, so what is left? That's it. You can just go ahead and notice that, okay, if x is equal to 0, then this just basically means A0 minus A1 minus A2 and so on, sure. Or if x is equal to 1, A0 by A1 into A2 by A3 to A4 by A5 and so on. So you can just go ahead and notice that these clearly aren't very useful, but they just exist for completeness. Okay, okay, cool. So again, starting newishly. Okay, so here, yeah, I've basically, the recursive definition is defined over here. And over here, you'll notice that, first of all, I've only used this exponent thing once, so there's no x business like here. And over here, instead, I've used the commutative operation is the inside as well. So I want to point out that these two things are equivalent. And okay, instead of proving to you that it's equivalent right out the gate, I will just claim that it is, and I will show you strong evidences. So you can go ahead and you can, like, maybe it's once I give an example, it's clear enough why this argument would extend well for higher and higher x's. So we know that, let's consider m is equal to e, like, unmistakably. So it's always, let's just implicitly assume that m is always equal to e. So a dot e, let's take it as 0 b, so that is just a plus b, right? Similarly, now what I'm going to do is I'm going to first construct it using this sort of method, like where I just line up all the exponents and all the logs, and then I plus, and I add up another line of logs, and I'm going to construct it that way. And the next thing, I'm just going to rephrase it in terms of the previous operation. That's it. That's all I'm doing. So you just have x log of a plus log of b. So you can see that this is exponent log of a e naught log of b. Make sense? Cool. Similarly, now let's consider e2b. So this is x log a plus log b. So again, it is of the form of the thing we saw earlier. So let's just take this entire thing and bunch it inside over here now. So that's all we're doing. So it is basically exponent of log of a e1 log of b. Does this make sense? I hope so. So yeah, you take e of x log of this thing. So this entire thing gets chucked into this a over here. This entire thing gets chucked into this a over here. And this chucking, like, not only includes that, also includes this exponent thing. So you're putting the entire thing inside it. Yeah, makes sense. So whatever was inside over here gets replaced by this chunk, where the log of a and log of b are it's instead replaced by log of a and log of b. Okay? And then you get this thing. So you would recursively just keep doing this and you would get your higher and higher operations. So this is my just evidence that these two things are equivalent, which is why I didn't want to spend much time on it, because it's trivial. But since this is like going to be backup for any presentations I give later, I should include it. Okay. Next thing. Okay, there's the fact that it's commutative over there. Not that deep. Here's the recursive definition over here that we just talked about now. Here is the negative ordered commutative operation. So what happens when you have minus x instead of positive x? And this is also where I start connecting things to tropical geometry. So throughout this paper, we denote log of am. Yeah, that's just another note about notation. So this part is slightly important. Okay, cool. So connection to tropical geometry. Via Maslov dequantization. So what Maslov observed is that when you take the limit of m tends to infinity of what was the, maybe if I just scroll down and find it, it would help me. Yeah, there we go. Okay. If you took the log to the base m of e to the am plus e to the bm, the whole into 1 by m, this limit as you take it goes to max of a and b. So the proof is sort of normal, like it seems trivial for this case, but the reason why I don't like this proof is because it's hard to work with when we talk about higher values of x. So the argument for proving this is by assuming that without, okay, why is this in my way? Yeah, okay. Without laws of generality, I assume that a is greater than b. And once I assume that, I just take the limit. So I'm taking log of m over here. And there's some business about saying that, okay, since e of a of m is greater than e of b of m, there's some business talking about how this thing as a whole has two terms that are comparatively growing. As m goes to infinity, this term grows faster than this term, and so whatever happens over here is negligible. So the argument is that as it tends to infinity, this term completely dominates. So you have e to the a infinity thing going on over here, and the idea is that, like, okay, this thing, this thing, as well as this thing, they all cancel each other out, and you just prop out an a. That's like the general feel of the proof about how it goes for this. So yeah, it's this argument about dominance. Now the reason why this argument about dominance doesn't work well is that okay, let's talk about how this relates to commutative hyperoperations, right? So as you can see over here, we've been talking about logs in E for quite a long time now, and I hope we can clearly recognize that this is of the form am. This is, yeah, okay, right. Over here we have m. Over here we have, I think, -1 over here, right? Yeah, -1, -1, and bm over here. What we're doing is taking this thing and we're taking its limit. Okay, I didn't leave myself any space. Limit as m tends to infinity. Oh, I forgot to multiply 1 by m over here as well. Okay, so this is how we were going about in Maslov dequantization. Now the thing is that Maslov dequantization gives us a way to go from algebraic varieties to tropical varieties. The reason is we take our we take our polynomial, we express it in terms of this sort of motion, this sort of like analogy, and then our operations that were previously addition and multiplication get converted to max and max plus operations, and those those polynomials also naturally change into what they were. So this is all very vague, the way I'm defining it. But what I want you to realize is that this is the way Maslov dequantization takes you from normal classical polynomials into tropical polynomials. Okay, so where were we? We were talking about, we were expressing Maslov dequantization in terms of Bennett statistics. And so, yeah, this whole argument about saying that one term is more dominant than the other is fishy, because the second you. Okay, here's why. Let me just scroll down. So, if I would have wanted to use this proof for higher and higher values of x, so let's take x is equal to 2 now. X is equal to 2. So in this case, I would take the limit of m tends to infinity, 1 by m into am of, what is it, m over here, we have 2 over here, -2 over here, sorry. We have bm over here. And this gets expressed as log of x am. Oh, that happens twice, right? Plus x bm, right? So this expression, the whole divided by m, so I'm just putting 1 by m over here. And so when I take the limit of this thing as m tends to infinity, I can use the same argument of saying that, okay, if I assume that a is greater than b, then I'm going to just claim that this term grows much faster than this term, which is true. And so no matter, like, again, because of this argument again, I can say it's basically the same as having only this thing and saying that this thing is essentially negligible, and then this log and x cancel themselves out, and I'm left with just, and this m over here and m over here cancel out, and I end up being left with limit is equal to a. So because of this, there's two possibilities, and we don't know which one to conclude, which is why we say that this proof is fishy. Okay, in its own sweet time, it will scroll down. Okay, there we go. So, two conclusions for this thing. So, either the first one is either this dominant term business is, what do you say, inconsistent, or for all values of x, if m tends to infinity, then we always get the same tropical semi-ring. So we get always the same min and max. So we always get the same max plus algebra. So we would have max over here, we would have plus over here. So to those who are familiar with tropical geometry, you will know of this correspondence. So there's two conclusions. The second conclusion says that there is only one possible tropical geometry. So it means that if we do this business of taking m goes to infinity, then if we, no matter how high of a value we give for x, unless we do something crazy like taking it to infinity, then they're all equivalent. So yeah, so we would have to do some genuinely crazy things for us to actually come up with newer algebras. I hope this thing gives some sort of framework to actually generalize it. So maybe by this thing it's clear that some possible directions is either to take x to some crazy value like infinity while you're taking m to 0. Some sort of combination like that may actually give rise to new operations. And if those prove to be the exact same as a tropical semi-ring, then that just further solidifies that tropical geometry is the best we can get at distilling information into something smaller. So, yeah, at least in this direction of negative Bennett hyperoperations. So I'm writing hyperops over here for hyperoperations. So yeah, this would be an interesting result on its own to show that there is only one tropical geometry and there cannot be more than one way to interpret it, at least if you go in this direction of the thing. So we were constantly going towards the negative direction. So we were going to 0, to -1, to -2, and to -3. And this line of thinking will just prove that no matter how low I go in the negatives, so if I consider negative hyperoperations, no matter how low I go, I will always get the exact same tropical semi-ring. And I will not get a new tropical semi-ring or a new version of, a new version of going from my classical polynomial to a funkier version where I get different kinds of information rather than the kind of information drop that is offered in tropical geometry. So this is another point yet adding to why this is the choice of having f is equal to exponent way earlier when we were considering f is equal to sine of x and f is equal to exponent of x, and when we were juggling between which of these functions is inherently better and an inherently better choice. This is another sort of justification as to why f is equal to exponent of x is a much more natural choice. Yeah. So, right. Okay. So the rest over here is just talking about what happens, as we go along that line. There's an error in this paper where over here this a to the m must be a into m instead of a to the m. So that needs to be fixed. It somehow has escaped us. Yeah. So with all this talk about tropical geometry and implications of using Bennett hyperoperations, only goes to prove that there's only two ways to further, solidify this claim, the claim that there is only one tropical geometry. The first thing that we would need to do is that we would be need to be able to somehow forego all this dominant term business, or we should make it more consistent or convincing, which it currently isn't to me, but at least it gives some for some explanation rather than none. So we are either looking for some sort of a more refined explanation of why we get max and why we get the max operation and the addition operation as a result of this limit, or and not or. The next thing we would need to do is that we would need to prove the same thing for sequences like our actual Bennett operations. So we were talking about negative Bennett operations, we're fine over there. We need to consider the positive ones as well, which just means our original non-negative Bennett hyperoperations. So that's x times over here log to the base m x times over here plus of a plus log m x times over here of b. Okay, so if we prove it for this as well, then we're golden. This is a strong enough It is strong enough evidence to show that there is only one tropical geometry, because we showed that for any other choice of f in that whole f of, oh wait, let me write that clearly. In this whole business where we took f of this and we took inverse of that, x times of a plus f of inverse of that, x times of b, we saw that in this whole business the choice of f equal to exponent is the most natural. Okay, and moreover, now when we consider these two different interpretations, so there's the positive one and the negative one, if we can show that for these two cases we always get the exact same tropical geometry, then we're fine. The only thing we will be vulnerable to is to really crazy things like this, because when we go in this direction we would have to worry about the rate at which we approach infinity, or the rate at which we approach the rate at which x approaches infinity and the rate at which m approaches infinity. So because if we take them approaching at the same range, at the same speed, basically it's not going to consider business where I first take m going all the way to infinity and then I consider x going to infinity. So what I mean by both of them approaching infinity at the same rate is that they're both at making the same progress to reaching infinity. There's no one that reaches infinity logarithmically and the other one reaches infinity linearly or exponentially. So that is the room for messing around with these different versions of dequantization. So the only way we can change how we the only scope we would have to change what kind of dequantization we have is by forcing x to have a different rate and forcing m to have a different rate. Those are the only two directions. And well, here's just 2-3 things I expect would happen. I expect that if if the rate of one is greater than the rate of the other, then I would expect that it should basically lead in favor of the one that is faster. So say, if we have some unexpected behavior when x itself goes to infinity, and we have our known behavior of converging into tropical geometry as m tends to infinity. So these are two different directions of us approaching to infinity, and if m goes there faster, then what I expect is that we will get tropical geometry, because we're approaching tropical geometry quicker than we are approaching whatever lies when x is equal to infinity. That's basically all the comments I want to say, because these two seem to be the most likely things that could happen. We don't know what kind of crazy things could happen, so what I would say is that the only way things can go fairly crazy is if these both have differing rates of approaching infinity. So that would rule out the possibility of one of m being strictly greater than x, or x being strictly greater than m, and this would rule out the possibility of them, like, tilting in favor of the other. So when m is approaching faster, then the entire algebra would tilt in favor of m to give us tropical geometry. So if we can avoid that by, like, messing around carefully, then we may get something that's different. And I just wanted to point out that this is the only possible way that we could. So unless you want to go with different choices of f, so if there's something more natural than this version of f, then that would be the way to go, and to show that okay, we get tropical geometry. But currently this is what seems like the best choice. So unless we can, like, definitively say that f of f is equal to exponent is like the best version of f we can take, until then we can't be sure, but there's pretty strong evidence that it is sure, that it is certain. Okay, let's delete this now. Now we start talking about the connection, and let me just have a quick peek at how long it's been. An hour. Okay, that's good, that's fine, because I'll just keep it uploaded later anyway. So yeah, the whole point of this is for a backup. So yeah, come, let's continue. So this is the part where we go from Bennett operations into Bennett statistics. So all this would mean is that mean is a pun. So all this would mean is that I'm taking my mean, right? Mean over observations, and I am just generalizing it to fit into the broader context of Bennett hyperoperations and Bennett statistics. So this is the kind of question we're dealing with here. So what does the mean? It's basically a sum, right? A sum of I goes from 0 to infinity, to n, not to infinity, of xi, right? Or more wisely, we should choose of ai, because you remember this x thing was all the way back there, and so it could lead to confusion. So let's disregard x over here instead, and let's instead consider ai, because we're used to using as ai as an operand. So we can re-express the sum. Oh yeah, it's also divided by the number of observations. So we can re-express this in terms of Bennett statistics by just saying that x equals to 0 in this case. X is equal to 0, n, I is equal to 0, ai into the inverse Bennett operation. So in this case, this whole thing gets chucked into a bracket, and outside I'm going to take the inverse Bennett operation. So that would be m x equal to 0 for this case, this specific case, of n. Okay, so yeah, you can see the correspondence between this and this thing over here. You can see the correspondence between this and this thing over here. The only difference is over here I've multiplied it with the inverse of this. In this case I'm directly taking the inverse. That's it. Okay, so as you can see, if I take away this assumption of x equal to 0, then I have my general mean. So let's just write that. Have I included notation? Okay, so let me just write it as is. Let's forget about actually denoting it with something unique. So this is what my operation would look like. Now I want you to remember that although I've explained this part well, not like well, but like I've explained it, yes, I haven't talked about what these inverse operations look like. I've given you an explicit formula about how to compute this part, but I haven't given you anything for this. Another thing is, this part also, I have not given you an explicit formula as well. I've given you an explicit formula for this part. So this part is fine. We need to talk about what this hyper summation even looks like. We need to talk about what this inverse hyper operation looks like. So let's discuss those two things. Let's discuss those things when the notebook decides it wants to delete what I want to delete, instead of selecting everything on my screen. Okay, there we go. Great. Looks like it made up its mind. Okay, let's just scroll way up here, because I don't want to be in that corner, and let's scroll way up here because I don't want to be in this corner either. Okay, so right, let's zoom in further because I don't want to write humongously. Really a mind of its own, this thing. Ah, there we go. Way better. Way better. Okay, so what do we mean by this thing when I take this and I put it like that, and I put an n on top, and I put an I equal to 0, ai on top? I have explained that it is equal to this thing. Oh, okay, a1 over here, and so on, right? But this doesn't tell you anything because you don't know how to take all of them together like this. All I've told you is that it's commutative. I don't know how. I haven't explained how to take it all together at once. So what this is the same as this over here. If it opens, that is something I could show. Yeah, these things. Yeah, this thing definitely has a mind of its own. So, right. Yeah, so we start by just solving what it would mean to solve this thing together, right? And then we can express this in terms of, okay, that was weird. Okay, we can express this in terms of what do you say, log. So I'm assuming an order over here, which is why I've taken this part separately. So I'm assuming that I do this operation first, where like I take a separately and I take this term separately, and then I open this term inside of this side. And so this is basically what I'm going for. I'm trying to prove that it's associative, that if I take this order and if I take that order, they're equivalent. And oh wow, it's gone. Okay. Yeah, so things crashed. Now I'm back. And so what I wanted to show is that it's basically the same as this expression. So since we've shown that this thing is associative and commutative, it allows us to assume that our sum that would have looked like this can be more clearly written down in this form. Let me just flip to the image. Yeah, there you go. Not there you go. Almost there you go. Yeah. So it's basically the same as the exponent x times plus the summation, not plus, of the summation I is equal to 0 to n log of x times of ai. Okay, so this thing can be re-expressed as this thing, and this thing, because of its summation inside, actually becomes computable, and this is just overall a lot more clearer than the previous thing. And so now the thing that is left to explain is the inverse operation. So if I have a and b, the only difference is that it is now, instead of an addition being in between the log terms, the log of a, log of a terms, and the log of b terms, you're going to have a minus sign. That's it. So you have log x times of a minus log x times of b. So you can solve for x equal to 0 and 1, and you can see that this is true. Yeah, for x equal to 0, you just get a minus b. For x equal to 1, you get a by b. Okay, so it checks out. So with that out of the way, we can be more confident in the operations that we're trying to work with. Okay. So now we actually define raw moments. So the mean is going to be where it is, right? We're not going to bother with the mean. We're not going to generalize the mean. What are we going to generalize then? We're going to generalize moments. So raw moments, central moments, we're going to generalize those two things. And once we do that, that's when we're going to just rephrase the mean in terms of these two moments. So raw moments are a power generalization of mean, just mean, and not deviation, I think. So it's just simply mean. So so a raw moment mu dash of r would have been defined as just the summation of xi to the power of r. And this would have been divided by n. Right? Makes sense. Similarly, we can define a hyper raw moment as it is poorly named over here, or you can better name it as a Bennett raw moment, because names sound better than childish things like hyper, or maybe it's cool. I would like to use hyper. It's just that if I use hyper over here, it gets overused very quickly, and so everything just starts with hyper, and so it doesn't give room to talk about things that get generalized again after using hyper operations. So the Bennett raw moments are just mu dash of r, p, k, and m. I've just stopped using x in the hyper operation things. As you can see over here, this is not x anymore, it's just p. So that's what the p is for. So that is equal to I is equal to 0 n xi to the power of r. The whole thing is now divided, would have been divided. It is now inverse hyper operationed, and now it has m over here, p over here, and it has n over there. Oh, p plus k. So this division business corresponds to this hyper operation. So we have now not minus 1, we have just 1 over here, and we have e over here, this summation thing corresponds to E over here, 0 over here. So as you can see, the 0 that was there over here bumps up to a 1, which is why we have a k over here. So instead of necessarily bumping up by 1, we can bump it up by any arbitrary number k. Okay? So that is, again, at the moment, it is a unnecessarily generalized look at things. And this is part of the reason we just wanted more flexibility, right? So this gives us that flexibility. You just plug in whatever values you like, get whatever values you, whatever, you can plug in whatever you like, you can get out whatever formulas you want, and the hope is that you get something useful from these things. Some actually useful information about whatever data you are observing. Yeah. Okay. Cool. So you can start at raw moments, and the central moment is just a deviation from a selected raw moment. So you can either like measure the deviation about the mean, which is what the central moment is, or you can measure a deviation off of any other raw moment that you like. So over here, mu r of, okay, let's just put that again, mu r of what is that, mu dash r naught p k m. This is just all the relevant coefficients just plugged in there for whenever you want to use it. So again, p denotes that the order of the hyperoperation we're at. So we have our sequence of Bennett operations. P just tells us at which step of the ladder we're at. K is going to tell you by how much you're stepping up the next inverse operation. So that's why you saw P plus K earlier. M is the base of all your stuff. So it is the base of your exponent thing, it is the base of your log thing. Okay? So, yeah. Let's rewrite this. So this can be expressed in I equal to 0. X of I, this is the x of I corresponds to our observed data, minus whatever our choice of raw moment is, the whole into r, and the whole thing is now acted upon. Let me just scroll a bit to the side. That would be preferable, but it does not seem to prefer that. Okay, there we go. Preference changed. Yeah, better. Okay. So this now comes over here. I still have the same base m over here. I can change that as well. So that's another added possibility for generalizing it. It's just that one claiming two different bases seems a bit extra. It seems a bit far-fetched. I wouldn't know what to do with that. I wouldn't even know what to try with that. And so then you have n over here. So this big thing is interacting with this single n thing, and yeah, everything seems to fine. So p is the order of Bennett operation, and yeah, you do know that, like, we can also say, like, we are all aware that we can take positive orders and negative orders. So I can have p is equal to 0, I can have p is equal to 12, I can also have p is equal to minus 4. So positive numbers, negative numbers, 0, they're all fine. And next thing is k over here. K is just how much I'm the order of the inverse Bennett operation. Okay, that's it. And mu dash over there represents the raw moment. R naught represents the order of that raw moment. So everything is sort of like, this is just the complete machinery for you to mess around and do whatever you like. And yeah, am I missing anything? No, I hope not. Okay, so let's talk about skewness and kurtosis. Oh, I don't know. I don't like to zoom out that much. Okay, cool. Select all cut. Yeah. Okay, so skewness and kurtosis are basically ratios of central moments. So, central moments or raw moments? Central moments, right? Yeah. So, now for skewness, I am going to consider beta 1 is equal to mu of 3. Okay, so let's just map everything to what it was. So R is equal to 3. What is 0? P is equal to 0. So 0 here is P. 1 over here is K. And M over here is E. Oh wow. Okay, cool. That whole thing is now squared, and it is divided by mu. In this case, there's a 2, and that thing is now R. Like, that is what comes in place of R. 0, that is what comes in place of P. 1, that is what comes in place of K. And M, E comes in place of M. And this thing cubed. So this is the same as taking your raw moment mu, what is that? Mu dash 3 divided by mu dash 2. This thing to the power of 3, this thing to the power of 2. Okay? So this is equivalent to this thing, this is equivalent to this thing. So in a general note, going more in the style of this notation, we can generally define, either we can define it as beta R1 minus R2, because I think this R1 minus R2 is more helpful to relate a bunch more of betas, or we can also note it as beta R1 comma R2. Just be mindful that, like, this is not the same as beta R2 R1. Okay, so yeah, we can consider these two equivalent notations for this, as long as we care about the order in which they're written and we don't abuse that. And the next thing is that what you will notice is that the order of the term is basically the same. So if I have something to the power of 3 at the top, something to the power of 2 at the top, and stuff like that, multiply. Over here, the total order is 6, because this mu 2, 0, 1 thing, what does it represent? It represents the raw moment of order 2. What is the raw moment of order 2? It is the summation of all observed data. That is, like, it is the summation of squares of all observed data. Similarly, mu 3 is the summation of all cubes of all raw data. Now, if I take at the bottom, if I take my mu 2, which is the sum of all square data, and I take that to the power of 3, its overall degree is 6. Similarly, if I take at the top my mu 3, it is the sum of all data that is, like, cubed. I take the data, the summation of all data cubed, and I square it, and my overall degree is now once again 6. And so 6 on the top, 6 at the bottom, overall degree is just 1. Okay, So that is something that is important to keep like preserved. Whatever coefficient I come up with should have this overall degree of 1. I cannot have a mu at the top that has a higher degree and a mu at the bottom that is a lower degree, or I cannot have any sort of like, mismatch in degrees. Both degrees at the numerator and denominator must be same. So, in line with that, we have defined A1 and A2. So, this A1 and A2 will become clear. It's just talking about the cross product. So, similarly, if I have something like AB plus C by D, and you can just cross product this and get it right. So, it's a similar deal with that. Instead, you could say, oh, it is the sum of, like, you can rephrase it in a more complex language saying that this is the sum of LCM of A comma D divided by D into A. Oh no, divided by D into D. Similarly, LCM. Is this true? I'm not sure if this thing is true, so I'm not going to go ahead and claim it. But I'm just trying to show. Maybe I'll come up with a better demonstration of that later. But what I'm trying to express over here is that. Okay, this thing is again crashing out. I'm not sure why it keeps saying this. But yeah. All I'm trying to express is that this A1 over here and A2 over here are going to be my exponents over here. And when you work it out for smaller values like 4 and 2 or 3 and 2, you will see that it's basically the same. We'll see for the second example, kurtosis is when you take mu to the power of mu 4, like mu dash 4, raw moments of order 4, and you divide it by raw moments of order 2. And for the raw moments of order 4, its exponent is nothing, it's just 1. For the raw moments of order 2, it is the sum of all squares of observed data. And so to get the degree to 4, you have to square this mu 2. So that's why you have mu dash 4 divided by mu dash 2 the whole square. Mu dash 2 square of mu dash 2. If I say the whole square, that means the whole fraction is being squared. So clearly, by this thing, you can generate as many different coefficients as you like. And the cool thing to note is that when earlier you were talking about R1 minus R2, this sort of notation is interesting because when we're considering kurtosis, we take the beta 2 comes from the fact that I'm taking something of degree 4 and degree 2. So we want to generalize that. We want to take something like degree 5, no, not degree 5 per se. Sure, we want to take something of degree 5 and degree 3, degree 7 and degree 5, and so on. So we want to put all of these things, so like 4 and 2 have a difference of 2, 5 and 3 have a difference of 2, 7 and 5 have a difference of 2. We want to put all these individual ratios under one basket and be able to collectively observe one kind of behavior from them. So this is the reasoning about why we would like to bunch them up inside beta 2. And the idea is that we would bunch them up inside beta 2 and we would study this set of beta 2s instead to talk about to find some interesting information about our observed data rather than talk about the observed data directly, which is like what we do in statistics anyway. So, right. Then we can construct our hyper operations of skewness, and we've just set k is equal to 1 for simplicity because, I mentioned about how k's are bumping up value, right? So when we're taking the hyper summation of order k, our Bennett operation of order k, we're taking a summation of that thing over all our observed data. So we're taking that oval thing over all our observed data, we would have taken the inverse operation, but the order of that inverse operation has to be greater than the order of the numerator thing. So this k is where that order of the thing becomes greater than the order of the numerator. And yeah, we do not know how to study the structure, so we've left it there. We've just put our findings over here and we've left it as is. Again, these are all open-ended, so whoever reads this paper can go ahead and see if this actually does anything on their data. This gives some new information that they didn't have before. So yeah, over here we just considered two different ways to study it. One way would be to take this set of numbers and to just condense it into one overall number that represents all of these numbers over here. So that would entail a measure of skewness. So we have a set of all possible skewness. So these would be a collection of all beta 2, such that over here you saw beta of R1 minus R2, right? And so in all these cases of like 4 and 2, of 5 and 3, of 5 and 7, in all these cases we have a difference of 2. So beta 2 is basically the same as beta 4 minus 2. It is basically the same as beta 5 minus 3. It is basically the same as beta 7 minus 5. So that minus 5 minus the whole 5 minus 3 business and the 4 minus 2 business and the 7 minus 5 business, that all goes into the subscript of beta. And so the idea is that I would bunch up all these different beta 2s, and then these would ideally be just numbers that I get from my data set. So I would chuck in my data set into this beta 2 thing. I would get a bunch of real values. And what's a useful way to study these real values? So one way we can go about it is by taking a measure. We would have to define a useful way to measure our skewness based on this overall values. Some interesting thing we could see is that maybe these values cluster up into a closed set of values, like say beta 4 minus 2, beta 5 minus 3, beta 7 minus 5. These three beta 2 values, they're all essentially beta 2 values. So these three values can maybe be really close together. So if I plot them all on the real line, they could be close together, and maybe I could make a statement that maybe I could say something logical by observing the fact that they're all close together. Or maybe some data sets may result in these different beta 2s being wildly far apart. And so if I have a measure that either sees how close they are or measures some inherent quality about them, I can find something useful to talk about its skewness, rather than this arbitrary decision of taking mu dash 3 square divided by mu dash 2 cubed. So that is one possible way, but that is more like it's more like a possible direction or just a footnote to be aware of when considering this. Okay, then we also propose a new way to estimate kernels, which is extremely complicated, and I do not feel like getting into it now because I didn't see evidence of it being being well suited. However, I put it there in case anyone comes across something that looks like this. They may find it useful to go through. So I try to do something similar to a Lebesgue measure over here, insist where I'm setting the function is equal to x, and I am seeing what happens, and what happens is somehow quite complicated. And so yeah, that's about it for this section. So I'm skipping over that section because I have no interest in going over it right now. The next thing is commutative hyperoperations on matrices. So let's talk about that. Okay. So where is my pen? Okay, there it is. Okay, so cool. So Bennett operations of matrices, I would have to take a matrix M and N, and I would have to explain what I mean by mx of this order. And another thing is matrices are not commutative. So I would have to explain if it's commutative or not, and if this is just useful at all. So to talk about commutativity, so we can express this as we've seen so far in all these, log m over here, x repeated, m over here, plus log x repeated, m over here, n over here. And so, right. So a log of a matrix can be approximated via Taylor series, right? And so can the exponent of a matrix. So the problem is when we're considering, first of all, repeated logs, because that approximation gets significantly worse, and when we're considering repeated exponents, because already the approximation was fairly flimsy. We It is hard to compute higher order terms, and these higher order terms come with more corrections. So it's not like we can just say that okay, whatever things these higher order terms are coming up with are negligible or something. We cannot say that. So because of which these two things present an issue. So one possible workaround, which is relatively hard, is through Clifford algebras. So in Clifford algebras, it allows us to define an algebra with I'm not sure what the notation is, but P, Q, and R. So P is the number of what do you say? It is number of solutions of x square is equal to -1. Q is the same thing, number of solutions of the form x square is equal to +1. R is the same thing, it is the number of solutions of x square is equal to 0. So this is the number of times we're considering the complex numbers, this is the number of times we're considering the split complex numbers, this is the number of times we're considering the dual numbers. And so the interesting thing is that since we can take any arbitrary P, Q, and R and we can talk about its algebra, each number from that algebra. Okay. So let's take some examples. So CL100 basically means I have one complex root, which means it's basically the same as my complex numbers in the first place. My numbers are of the form a plus ib. And the interesting thing about complex numbers is it has something called a matrix representation. And this matrix representation allows me to write a plus ib in the form of a 2 by 2 matrix. It just looks like a minus b, b, and a. Right? Similarly, CL, what is that? 0, 1, 0 is the split complex numbers. This is numbers of the form generated, numbers of the form a plus jb, which is the same as a b, oh wait, no, yeah, ba, that's right. Okay. And lastly, let's not talk about what R is, because that is not that interesting, because the point that I want to say is that each Clifford algebra has a matrix representation. And so the idea would be that it is easier to take hyperoperations of these things, because exponent and logs are much better defined within these algebras than they are defined for matrices. Because we talked about the issue with approximating it. So solving, like finding the log of x of like some matrix forces me to approximate it using a Taylor series, which we know is unreliable from experience. So what we would prefer to do is we would prefer to take the log of this complex number instead, or some number from any given Clifford algebra. We can take the log of that, and because we're taking log of some hypercomplex number, its logarithm is well defined, and like I can compute it analytically rather than having to approximate it with a Taylor series. So because of this, it becomes like knowing what this matrix is becomes easier to talk about. So yeah, the harder idea is that okay, if I have some number with some random imaginary unit, let's say z, be like this, okay, and we know what its matrix equivalent thing looks like, and we know how to do hyperoperations between these matrix equivalent things. So we know how to go from here to here. What we do not know is how to go from here to here. So if we can start from the matrix, which is where we're at, we want to do this thing. And so our solution is to take this thing, convert it into its respective hyper complex number, take this thing, convert it into its respective hyper complex number, and then actually perform the operation between these two things, and then represent that as a matrix. So this would be one approach. This would require us to be amazing at doing Clifford and at converting matrices into its original Clifford algebra. And that would be interesting but extremely challenging, because we don't know if we know that every Clifford algebra has a matrix represent theorem. Wait, let me see if that's an actual theorem. Hang on. Hello. So let's continue. So the whole thing about bypassing the issues with approximating our matrices with Taylor series is that we would have to like we would have to find an equivalent algebra, and then we have to go back into this. So there's two ways to go about it. If we have matrices of like this that have really good structure, let's say this is 5, 6, 7, 8, 9, like this. Something has really good structure like this, then maybe we can assume that this represents a number with some unit, like some unit over here, 2, some new unit over here, plus 3, some unit over here, and so on until you go to 9 and you go to the 9th unit. So this would be a new algebra that can be represented by this. We claim like this. So one thing that I forgot to mention is that every matrix has an algebra. So every Clifford algebra has a matrix, and from every matrix we say something called every matrix representation is faithful, which means that more or less it is weaker than a one-to-one correspondence. More or less every algebra would correspond to more or less every matrix representation over here would correspond to an algebra down here. That's the claim. Okay, so this is a complicated way of going about it, because that would mean that we would have to find a way to exploit the symmetries of a matrix to actually get a Clifford algebra out of it. Because sure, we can have, okay, so I would like to show you two cases, right? Two possible strategies that we can have that would like explain why it's difficult. to go in this route. So let's go a little further. Let's consider simple matrices. That big 1, 2, 3, 4, 5, 8, 9 voila matrix is just there to explain what something with nice structure would look like. Now I would like to show you what something with like exploitable structure should look like. So say I have something like A, B, B, A like this. This would correspond to something like A plus JB, where J square is equal to 1. Similarly, what was I saying? Yeah. What if I had something like A minus B, 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 A plus B? So in this case, I would have to consider a different kind of Clifford algebra. Yeah. So where is it there? Yeah. So if I had this case instead, what sort of number should I get as a result? I may have some sort of really weird unit over here that does not satisfy something this simple. I may have some other even weirder unit over here that does not satisfy again something as simple as this. So this is the reason why it would be difficult. So first of all, in this case, if I gave you a matrix that looked like 1, 2, 2, 3, not 1, 2, 2, 3, if I gave you something that looks like 1, 2, 2, 1, then you would immediately look at me and say this looks like 1 plus 2j. But if I gave you a matrix that looks like 1, 2, 2, 3, then this would look something weird like that W plus, what do you say, 2V. So we don't know. So this case, it is clear. I know what this is. This is my split complex numbers. I am very well familiar with this. I would know how to do exponents and logs with this. But this, I'm not even sure what it is. So we don't know if this is a Clifford algebra. We don't know if this is a representation of a Clifford algebra even. And so because of this inherent complicatedness of it, finding this relation is much harder than being able to just simply draw a correspondence between my 2 by 2 matrix over here and the split complex numbers over here. So because of this difficulty, I going this route of converting it into Clifford algebra and then doing it is also difficult unless we figure out a really general way of converting any matrix into some sort of algebra. Doesn't necessarily have to be a Clifford algebra, because a Clifford algebra means that I have a certain number of complex roots, a certain number of split complex roots, a certain number of dual roots. So this Clifford algebra basically gives you freedom to work with a number of different roots. So the number of how many roots there are is what changes the things in Clifford algebra. That is your main focus in a Clifford algebra. However, in this case, we don't even know if it is a Clifford algebra to begin with. So that is why Clifford algebras could be a dead end. That is, like, it is more of a rocky road than it is a dead end. So it would be hard to go through. The next way to go is by generalizing the Euclidean product. So in this case, we start off from vectors. So we'd say A is like A naught, A1, A2, blah blah blah, AN. We say B is equal to B naught, B1, la la la, BN. Okay. And so what we're going to do is we're going to define what it means to do Bennett operations on A and B. So we can call this the generalized Euler product, but Euclidean product, but that name is used a bit too often for a number of different things. So let's call them Bennett inner products. Yeah, so Bennett inner products. So this would basically mean A into B. And this thing we're going to talk about what we mean by AM. Be like this. Okay. So let's scroll down a little more. Yeah, hyper inner products. Oh, my bad. This is dot product. Sorry. I was thinking about cross products for a second. Yeah. So A comma B, like the Euclidean inner product, gives me a summation of all the products of these terms. Right? So I goes from 0 to n. This is my Euclidean product. So a generalized product would look like this. This is very like, pump and our standard notation again. So our hyper summation notation. So again, we're going from n. We're starting at I is equal to 0, and we're taking the Bennett product of these things, or like I'm just putting Bennett over there to explain that this is again like A into B, right? So we want like AI into BI, right? So this multiplication we want to truly be like general. So this would instead mean A of I into okay, this seems a bit wrong. What I mean over here is, yeah, that is definitely wrong. So I would mean X, oh no, God, okay, K of M BI, like this. So again, K is my jump by how much I scale up the product. So this gives me more generality, but to be more faithful to what is there, that is to be more faithful to the actual Euclidean product, we should set K is equal to 1. And so if we set K is equal to 1 and we consider this whole thing, it's equal to A of this at M and 0. Okay? So this is how we generalize it for vectors. Now, using this generalization of vectors, now we can talk about matrix multiplication. So in the similar spirit of how we... Okay, help me. Okay, I don't know what happens to this laptop most times. It seems to have its own head. Cool. Okay. So, matrix multiplication. In this case, instead of having a vector A and B, we're going to have matrices A and B. That is respectively given by the elements I, J, like this. Okay. So, right. So now the element of A, okay, wait, let's just put this in brackets again. So this is MXB over here, and I have the ijth element. So this is equal to when x is equal to 0, it is equal to just a summation of aik bkj summation overall ijk until n, right? So, or not all ijk, just k from 0 to n. And similarly, in that same spirit, when x is equal to x, so some arbitrary integer, yeah. So the Euclidean matrix multiplication is given by, the Bennett matrix multiplication is given by this for the ijth term. It's given by the summation for any general x. It is given by not the summation anymore. It is now given by the hyper operation mx with aik the whole of mx plus 1, so we're bumping it up by 1, and then bkj from k is equal to 0 to k is equal to 9. Okay, so this gives you your ijth element in this thing. And yeah, we can talk about inverses and stuff like that. We wouldn't be sure about what an inverse would be with respect to these operations, which would be one thing that's interesting. And yeah, since we got the hyper operation between matrices, we just went ahead, we defined covariance and correlation between two vectors. That's simply just the product of two, how do you say, differences. Over here, it's just re-expressed in terms of hyperoperations so that it is available for higher interpretations. So instead of actually explicitly writing down the covariance, over here we wrote it in terms of our general thing. So you can see over here it looks like the inner product with the k at the side over here. So the k over here is actually meant to represent the m in this place. So let's rewrite this a little better. Let's scroll down, and when the notebook decides to scroll down, then we will rewrite this better. Hello. Yeah, there we go. Cool. So yeah, we have two vectors, sigma x and sigma y, that represent the corresponding differences. So sigma x and sigma y are what we call our deviation vectors. So you can see we have our individual observations, and they're just translated by x bar. Over here again y bar. So yeah, these two are individually vectors that belong to Rn. And so the whole business of taking two vectors and doing mx like this, x was a poor choice of this, let's say p over here, so sigma y. So if we take two vectors like this, I'm just saying that it's the same as this. That's it, just a notation change. That's all that's happened in this article over here. And so with this notation change, I can, I can compute the generalized covariance. So the generalized covariance denoted p over here, over there it's k. So it's just x comma y is given by the deviation matrices like this, and you have your e and p plus 1 and over here. So like I've said earlier in this talk, whenever we are indecisive of what m should be, we just say okay, m is going to be equal to e. That's it. Then similarly we can generalize Karl's coefficient of correlation by using this k covariance and its k variance, etc. and so on. The k variance is given just by taking the covariance of itself. So I can similarly get the variance of x like that, I can get the variance of y like that. And what else is left? Yeah, that's it. That's basically it. So with these definitions, we finished the paper. And so the next directions of the paper, so further goals is to one of the first things would be coming up with a way to go from any arbitrary matrix to some sort of relevant algebra where I can do something. So in this case, I'm writing that down as a Clifford algebra. Because the reason is because we would be studying how to go from a Clifford algebra to a matrix representation more clearly. Then the next thing that we would want to understand is we would want to compute these Bennett moments, Bennett central moments and Bennett raw moments for families of distributions like I don't know, Gaussian ones, say a Gaussian distribution, say a uniform. We would start with a uniform distribution, then we'll go to Gaussian, and similarly we can go to I don't know, gamma distribution, anything. We want to assume a Gaussian uniform and a gamma distribution. We want to take we want to work in those systems and calculate whatever we get for mu dash r and so on in those cases. Then what else is left? Let's see. This kernel thing is practically finished. I wouldn't work on it more. It's simply there, as I said, just to provide something extra. Yeah, we would need to find a way to measure skewness from our actual set of values. And lastly, let's just scroll up further while this thing takes its time to scroll down. So, what else is left? That's basically it, right? Yeah. Hyper raw moments, that's it. So, in the next part, which I will continue now, I will talk about the connections between this thing and Mazda dequantization. So, I will pause now, I will open that paper, and then we will start now.